Our topic today is designing resilient transportation networks with GIS, and it is co-hosted by Esri. Our presenters are Terry Bills, Toria Lassiter, and Christopher Dorney, and I will be your host and moderator today. For those of you that don't know me, I'm Courtney Arena. I'm a principal environmental scientist with Gannett Fleming, and I work and live in the South Florida area in West Palm Beach. I work a lot with FDOT on a variety of different types of projects, and then other state and federal agencies here in Florida and throughout the Southeast. And I've been a NAEP board member for, I'll just say 10 years. I stopped counting after 10 years. So we wanted to just thank Esri. In 2021, the NAEP and Esri created a partnership. And so you'll see a lot of collaboration in our programs and content. That includes today's free webinar. And then also in terms of upcoming events, we'll see Esri involved with our NAEP 2022 annual conference and training symposium, which is planned to be in person, which is exciting, in May in Fort Lauderdale, Florida. So registration will be opening soon, and we hope to see everyone there in person. I'd also like to, in terms of opportunities to get involved with NAEP, we have a transportation working group, and this group provides a space for transportation-focused dialogue related to how we operate as environmental practitioners within the industry. Each working group session provides key topics for discussion to share new knowledge related to the various modes of transportation, including transit, rail, airports, and highways. Some of the latest key issues in the industry are focused on transportation safety and improved bicycle and pedestrian facilities. The working group is an organized team. They're committed to the research and development of the transportation industry, and their effort is centered on continuous dialogue, conversations, publications, and white papers with the goal of advancement of environmental professionals as leaders in the transportation industry. So if you're interested in joining that group, there's some instructions on the slide, and our working group leader, Caroline Lavenda, will add you to the list. Really quickly, I'd like to also, another NAEP benefit that we have, I'd like to give a quick shout out to the EPR, Environmental Professionals Radio. If you have not tuned in, I suggest you do. They have a lot of great speakers, and it's actually fun. So they've been producing podcasts for at least a year now. And so there's a lot of different episodes to choose from. One of my favorites was when they hosted Dawn Wright, Dr. Dawn Wright, the chief scientist from Esri, and she shared her story about deep sea discovery, her love for Legos, and her current role with Esri. And lastly, just a couple of benefits to keep in mind. For the NAEP members, you have free access to NAEP publications, a discounted conference registration, discounts on webinars, courses, seminars, and workshops, access to NEPA archives and other environmental reports. We have a career center. There's member directory access and networking opportunities. And now I will go ahead and I'll introduce our three speakers. We appreciate their time today joining us for this timely and interesting discussion. We have Terry Bills. He's the Global Industry Manager for Global Transportation Industry Manager for Esri. We also have with us Toria Lassiter. She is the Assistant Division Chief of the Maryland Department of Transportation and State Highway Administration. And we also have Christopher Dorney. who's the Director of Climate Resiliency and Sustainability with WSP. Thanks again for joining our webinar today. Just a couple of really quick housekeeping items, and then we'll get to our speakers. Just so you know, all attendees are muted. You can ask questions by typing in the question and answer section on the control panel. You can submit questions anytime during the presentation, and we'll hold them to the end and ask our speakers. And the NAEP office is monitoring the question box and will be available to answer any technical questions or technical difficulties that you experience during the webinar. So there'll be a brief pause and we'll switch it over, and Terry's going to start with his presentation.
All right, thanks, Courtney. First off, I'd like to thank the National Association of Environmental Professionals for hosting this webinar today on what has really emerged as an issue of central concern, not only to the transportation, but also the environmental community. And that is, how can we plan for and mitigate the impacts of climate change on our transportation infrastructure? And I'd like to thank all of you for taking the time out from your day to attend this webinar. So our goal today is to give you an overview of the scope of the problem, an overview of the methodologies that are typically used to analyze the climate impacts on transportation, and to present some of the best practice examples from several of the studies that have been conducted by the state departments of transportation. So let me start by highlighting this quote from the Federal Highway Administration, that indeed issues of climate resiliency will be some of the most vexing issues facing the transportation community in the future. And I think vexing for several reasons. First off, we're really dealing with an uncertain or an imprecise future, which makes it all the more difficult to plan for. But then also because there is still really a level of contention over both the causes as well as the impacts in the political community. That said, in the new bipartisan infrastructure bill that was just recently passed, it did allocate $47 billion to state and local governments to help them plan for and to mitigate these climate impacts on their communities. So there is a commitment at least to put a down payment on what will ultimately be needed to harden our transportation infrastructure. And quite frankly, I think that the impacts of climate change are going to likely dwarf our current disruptions associated with COVID. So to set the context for the scale of the problem, let me start out by pointing out that in 2020, we set a new record for the number of climate-related disasters, costing over $1 billion. And in 2021, we're on track to exceed that record as well. According to a recent report from the UN, there's been a staggering rise in the number of such events globally. Hydrological events have quadrupled since 1980. And in fact, they've even doubled since 2004. And the same with climatological and meteorological events have also doubled in that same period. The total cost of the 22 events in 2020 totaled over $95 billion and resulted in 262 deaths. And while 2020 contained the largest number of events costing over $1 billion, It was actually in 2017 that was had the highest annual cost of disasters, and that was just under 322 billion. And that was really largely driven by the costs of hurricanes Harvey, Irma, and Maria. And these are costs that really overwhelm the local responses to recover from these events. So, for example, in the aftermath of Hurricane Harvey, the Houston Area Council of Governments estimated that it was going to cost $3 billion to repair and to mitigate the risk of future flooding just for the Houston area alone. Similarly, Hurricane Irene in 2011 washed out more than 2,000 roadway segments, undermined more than 1,000 culverts, and damaged more than 300 bridges just in Vermont alone. And the costs to rebuild everything in Vermont were estimated at roughly $1 billion. And these are just the costs of the infrastructure alone, and really don't include the impacts on supply chain, on the businesses, and on the lost revenue from the storms. And NOAA estimates that over that same time period from 1980, that we've spent actually 2.1 trillion on such climate events in the US. And current estimates are that at least 25% of all of our critical assets in the US are at risk of failure due to flooding. And we've certainly seen concrete examples of that in the US this year, not only in Michigan, but across the US, with over 27 major flooding events to date in 2021. So let me say a few words about the role of GIS in climate resiliency studies. First off, there's wide consensus really that GIS provides the foundation for much of the analytical work in understanding these impacts. But I think probably just as importantly, or perhaps even more importantly, is the role that GIS plays in effectively communicating climate impacts to policymakers and to the public. And GIS is uniquely capable of clarifying and really of presenting complex information in ways that make the analysis not only more understandable, but ultimately that can help drive action, as this quote from Dr. Hayhoe attests. So to start, and well, I think Chris will go into greater detail on the methodology that he's used in a number of climate resiliency studies. I did want to give you kind of a 30,000 foot or high level overview of kind of the standard workflow associated with understanding and analyzing climate impacts on transportation infrastructure. So starting on the lower left, we really need to understand the location and the condition of all of our assets. And while that may seem very straightforward and straightforward enough, the reality is that many transportation agencies really don't have a good inventory, and especially of their smaller assets, things such as their culverts. And in fact, several of the climate resiliency studies have found that culverts are actually incredibly critical in understanding the risk of damage during hydrological events. So much so that the planning director at the Vermont Department of Transportation actually calls culverts the unsung soldiers of climate resilience. And similarly, at Colorado Department of Transportation, they found the same thing, the importance of culverts. And so as a result, they had to send out field crews to collect culvert information for their state highway system. So once we have that complete inventory of our assets, then we need to understand the criticality of those assets. And by that, what we mean is how many people would really be impacted if that asset failed, and what would be the cost to society and the disruption to supply chains. So this analysis in some cases can be quite sophisticated. We can use really sort of transportation models, or they can be simpler using expert opinion. But it really is important to help us understand the role that each of those assets plays in the overall transportation system. And then moving up to the top level, we need to understand the nature and the likelihood of future climate events. And so the impacts of climate change vary widely, depending upon where on the globe you are, and even within the US, the impacts will be quite different. So typically what happens is that there's an effort to what we call the downscale, the global climate change models, to bring greater specificity to really sort of understand your regional impacts. And normally that downscaling exercise is performed by a local university, and it's really designed to help guide agencies with respect to the nature and the likelihood of future climate events. And it's at this point that we really sort of define the various scenarios that are appropriate for the individual regions, and really to define the range of scenarios that will be studied. And then we really want to overlay that information on the specific topography and on the environmental context of the region to help us really define more detailed scenarios and specific impact scenarios. So we need, again, in GIS terms, we need a digital surface and an elevation models, terrain models. We need riverine and other environmental layers, really to help us understand the context and the likely impacts from future climate events. And then we generally look at various scenarios, including 50-year and 100-year floods. But ultimately, these events are occurring with much greater frequency, such that it's really becoming increasingly difficult to know how to define a 100-year event. And as we're going to see in the Maryland case, not only did they model a large number of different scenarios, but they even included a 500-year inundation scenario. And so we want to model a range of scenarios to help us bound the risk so that we can understand the wide range of possible impacts. And from those different scenarios, we can now begin to understand which of our assets are at risk or the relative vulnerability of those assets. And so we also generally want to understand the costs associated with those various scenarios. And in fact, some agencies actually want to understand the cost to buy down that risk or to calculate the return on investment from hardening the infrastructure ahead of a future event. And then that analysis really ultimately needs to drive the changes in the way that we plan, the way that we design, and the way that we maintain our infrastructure. And again, as the planning director at Vermont DOT said, the way that you bring resilience forward is to integrate it as a part of what you do every day and not to have it as a standalone program. And I think you're going to hear that both from Chris and from Tori as well. So a couple of quick examples, and then so the first example really comes from Vermont Agency of Transportation. That's really done some path-breaking initial work and their development of their transportation resilience planning tool. And in the case of Vermont, really the major threats were from riverine flooding, but part of what distinguished their analysis was that they looked at not just inundation, but in fact also the erosion and the deposition potential in their analysis. So as you can see in the matrix on the right-hand side, each asset is ranked into a matrix based on its criticality and its vulnerability. So we're looking at, in this particular case, a bridge at high risk and high vulnerability. Really the focus then in the case of Vermont was really on their roads and their bridges and their culverts. And this framework is now being extended to help even the utilities in Vermont also understand their risk. And for each asset, they also define a series of potential measures and strategies which can help mitigate that risk. And this is designed to help all the local jurisdictions in Vermont understand the criticality of or the threat to their assets, and ultimately to help them prioritize their capital improvement plans moving forward. So the next example comes from the Colorado Department of Transportation, and their analyses conducted really after a series of devastating floods in 2013. So their analysis looked at a series of potential disasters, include everything from rock slides and significant flood events. And they, again, analyzed in terms of the threat and the consequence. And they looked actually in 1 mile segments of the roadway. And in their case, it was very specifically designed to develop a cost-benefit analysis to really sort of help guide them in their maintenance and in their infrastructure planning. Much like Vermont, the goal really was, how do they incorporate this climate resiliency into all of their work processes? So the next example comes from Maryland, and I certainly don't want to take away any of Toria's thunder, but I do want to point out really the outstanding job that they did in terms of defining a wide range of scenarios and the ease of use of their climate change vulnerability viewer. And most of these applications are actually publicly available, publicly facing. So I have put the links on each one of the slides, and I would encourage you to go take a look at these. And then finally, the last example comes from Atkins, and they've actually built a city-level simulator to help cities understand the risk from a variety of climate-driven events, and really not just the impacts on their transportation systems, but across all of their assets. And then finally, if you'd like to dig a little bit more, we do have an ebook that and I've put the link, and we will put the link in the chat box as well, that really sort of goes into a little bit greater detail on each of these. So with that, I'm going to turn it over to Chris, and he's going to talk about the work that he did for the state of Minnesota. So Chris, if you want to take it away.
All right, thanks, Terry. Let me share my screen here. Are you able to see my screen?
Yep, yes.
Okay. All right, yes, I'm going to speak today about work that's actually ongoing for the Minnesota Department of Transportation, where we're actually looking at future climate change impacts on flooding to their culverts and their bridges. We'll start by talking through some context of the project and the goal of the project. Then we'll jump to the exposure analysis to flooding. And from there, we'll talk about some of the risk calculations that we're doing to help them prioritize where to take action first. Before we dive in, just wanted to make everyone aware there's typically two scales to the work we do on climate adaptation. And one is a systems level vulnerability assessment scale. That's sort of looking at an entire community, or in the case of a Department of Transportation, an entire transportation network to determine where are the areas of concern, and prioritize where you're going to take a closer look first, because there's going to, unfortunately, likely to be a lot of areas of concern. You need to do some prioritization. That's what we're doing for Minnesota at this point, but that will move eventually into the next phase of work, which is what we call project level adaptation assessment, and that's where, once you've identified those existing assets that are at risk, you figure out what's the best thing to do about it. What's the best course of action to take to adapt that asset? And that can also be done for any new project that's going on. So Today's conversation will be focused on systems level vulnerability assessments, but there's a lot to talk about with project level assessments as well, at least in terms of my presentation here with MnDOT and that work. So when it comes time to do a systems level vulnerability analysis, there's a few different approaches that have been taken across the country over the past 10 or 15 years as this field has sort of taken off. Some of the earliest approaches were stakeholder driven, where folks would often fill out a matrix of low to high risk based on just a qualitative assessment of information and knowledge available to them. That's evolved into kind of what is the state of the practice now, which is the indicators approach. And it's essentially creating, taking a bunch of metrics and creating an index for each asset that says what's the level of vulnerability of that asset. And we actually did a previous project with Minnesota DOT using that approach in a couple of their highway districts. And then there's also the quantitative risk approach, which is sort of the more cutting edge approach, I would say, at this point, where what we try to do there is actually quantify the costs of impacts if no adaptation actions were taken. And then wherever the costs are higher, that becomes your way to prioritize. Whichever assets have the highest costs become the highest priority. Just to give you a quick sense of where we are, what we had done with the indicators-based approach, though, this is going back to 2014. This was an FHWA pilot study, funded pilot study that we did with Minnesota Department of Transportation. We had several different asset types, and we looked at all these different variables for each asset. We calculated these. You can think of these as attributes in an attribute table. We obtained or calculated each of these attributes and then put them together and ranked into an index that ranked assets from 0 to 100, and we did that again in a couple of pilot districts. When it came time to do this study, this was a few years after that, and new techniques had emerged, and we said let's push it to a quantitative risk approach and try to do things that way. And that's what I'll talk about today is this quantitative risk approach. And again, what we're trying to do is calculate the expected costs or risk to each asset from the climate stressors if no adaptation is taken. Those costs may include, and they do include for this project, both the physical damage and repair costs to MnDOT themselves, and also the cost to systems users from that outage. There are some advantages to the risk approach over the indicators approach. It makes the link between the hazard, the impact, and the consequences a little bit more explicit and less fuzzy than with some of those other approaches. In some ways, you can argue it's more relatable and actionable to a DOT engineer, for example, because of that connection that's being made more explicit. And you have to get into a little bit of engineering to make it real and be able to make sure you fully understand these impacts. And it also provides dollar-based outputs, which we believe are a bit more relatable to policymakers as well. Kind of speaks their language than more so than, say, a bit of an abstract index. So our goal here was to develop and pilot test an approach that's capable of efficiently quantifying the risk, both now and in the future, of rearing and flooding to eventually all of MnDOT's bridges and culverts, which there are over 32,000 of them. But we started small on this project. We're just looking at 22 assets to do a pilot test, include 6 bridges and 16 culverts. We started with the exposure analysis, and one of the first tasks there is to develop precipitation projections. We developed them for several different return period events. You can see them listed on the slide here through the end of the century. Those are all daily precipitation projections. And we did it for a couple of different climate change scenarios, a moderate and a high. And that's to bound that range of uncertainty, as Terry was talking about earlier. So you can see generally over time, regardless of which scenario we pick, the lower or the higher emissions one, we do tend to see increases in precipitation intensity throughout the state. And that translates into changes in peak flow, which is our next step to try to quantify. And for this, we developed projections of all these different return period peak flow events at each asset. And we did that for each scenario, and we did it through the end of the century. And that was done through a process where we used the USGS StreamStats program, which provides current peak flow data at a point you place on the map. We were able to harness that in an automated way through their batch processor, and then do a scaling approach to take precipitation projections and see what impact that might have on flow in sort of a rough sense, planning level sense. And we can, for each asset, come out with a graph like this, which shows the change in peak flows for a particular return period event over time under the different scenarios that we analyzed. From there, we do a hydraulic analysis. And for this, we've actually developed sort of a custom-built GIS processes and a HEC-RAS query, HEC-RAS software, essentially, that enables HEC-RAS to be run in sort of a batch processing mode for thousands of assets at a time. Again, not something that you would use for design, but for a screening level, a systems level vulnerability assessment like this, it's good enough. And running that tool, we're able to get a variety of different outputs, like water elevations upstream of each bridge and each culvert, flow velocities, and what have you. And that's done for each return period under each time, under each scenario for each time period into the future. And then what we do is we report that out for each asset, and we have what are called exposure summary tables here, and these basically show for each of the different scenarios what the flood elevations are, and through some color coding here, hopefully able to quickly determine when you start seeing impacts to the asset from different return period events. Impacts being defined in different ways, but they could include water hitting the bottom of a bridge deck, actually overtopping the approachway, or actually overtopping the bridge deck itself. So we have different colors here to denote that. And then this particular project, unlike some others, we're not actually mapping the floodplains. It wasn't part of the scope, but we are able to take those flood elevations and use the LiDAR data and put them over top the roadways in the vicinity of the asset, the roadway of interest, and find what the flood depths are over that roadway for the various scenarios. So we take all that information that's been done at this point in the project, and now we're working with MnDOT on the risk calculations to help take that exposure information and figure out what are the consequence costs of that, and again, that's going to be used to help prioritize. So again, trying to estimate damage costs at each assets from the projected flood events. We have a few different models that we're building out. One is a roadway damage model, which covers the approach roadways. For that, we look at things like the pavement delamination potential, embankment erosion potential. We have a culvert damage model for culverts that looks at the culvert itself, and sees if we lose it because of there's too much embankment erosion, or you have erosion around the outfall. And then we also have a bridge damage model for bridges that looks at pavement delamination on the bridge, if water gets over the deck, other potential deck damage or displacement, and some scour considerations as well. We're also layering in user impacts, as I mentioned, not all of them, but some of them. And we're doing that through leveraging some of the routing capabilities and network analyst hazardous network analyst through a detour routing tool that we've developed a script for. And that's going to take, traffic volume information and combine it, with that network redundancy from the detour routing, along with some, assumptions about how long the road may be out for various levels of damage, and assumptions about time, fuel, and operating costs to basically, provide that estimate of a user cost per event. And then what we do is we have another set of algorithms that basically take those physical damage and user costs and combine it with the likelihood of each event to calculate risk, which is essentially a dollar value of an estimate in any given year. What is the cost to be expected from flooding events, and then we do some discounting, and we're able to essentially, get an estimate of what those costs will be from now into the future under each of the different climate scenarios. And we find the area under this curve essentially, and that gives us the total expected flooding costs through the end of the century. And from that, we can use that again to prioritize which assets have the highest costs. And eventually we hope to get to a table something like this, where we can have each asset as a row here, and we have costs, the total cost through the end of the century under the different scenarios. And we can break that down into agency and user costs, and we have a confidence limit, upper and lower confidence bounds on that as well. And these costs can be further disaggregated by year if there's interest in that. And to address the timing of when you would want to adapt a particular asset, or when you'd want to flag something for, hey, we need to take a closer look at this, let's move it to a facility level assessment. We'll work with the agency to basically select a risk tolerance threshold, which is basically an acceptable dollars per year of risk. And once you cross that threshold, and we'll flag that, and whatever the first year that threshold is crossed, that's when that asset becomes a priority for taking a closer look at things. So assets that actually get that flag pulled sooner would be a higher priority than those that get it pulled later or maybe never. So I'll leave it at that. Here's our contact information for myself or our project manager, Jeff Meek at MnDOT, if you're interested. But for now, I'll pass it over to Toria to talk about Maryland's approach.
Afternoon. Let me share my screen. Okay. Good afternoon. I'm Toria Lassiter, Assistant Chief of the Innovative Planning and Performance Division at the Maryland Department of Transportation State Highway Administration, or MDOT-SHA. And I'm glad to share the work that we do through MDOT-SHA's Climate Risk and Resilience Program to support the MDOT mission to provide a safe, well-maintained, reliable highway system that enables mobility choices for all customers. Through our program, the Climate Risk Resilience Program, we look to promote climate education, communication, and data sharing among state and local transportation stakeholders, build an understanding of the vulnerability of the statewide transportation infrastructure to climate risks and hazards, and identify potential mitigation options, and integrate consideration of resilience in transportation decision making. So Maryland is a relatively small state, ranking 12th smallest in the U.S. by landmass, with a very diverse topography ranging from sandy dunes in the east to low marshlands with abundance of wildlife in the Chesapeake Bay and to rolling hills in the Piedmont region, and forested mountains in the west, Maryland also has approximately 3,100 miles of coastline, which is particularly susceptible to the effects of climate change related hazards like sea level rise, storm surge, extreme high tides. And our state has lost 13 islands to sea level rise and land subsidence in the last century. Sea levels in the Chesapeake Bay have risen by a foot in the last century. And we have other islands at risk. And in fact, while sea levels are rising worldwide by an average of 1/10 of an inch or 3 millimeters per year, in some locations of the bay, the Chesapeake Bay, relative sea level rise, the relative sea level has been rising by 4.6 millimeters per year because of this. So we also see like 70% of flooding statewide happens inland and can be attributed to extreme precipitation and riverine flooding. And so with Maryland being in the top 20 most densely populated states in the US and having a little over 71,000 lane miles of road and over 5,000 bridges, MDOT has been for over a decade working in partnership with other transportation agencies to address the challenges of maintaining the state transportation infrastructure in the face of climate change related hazards. So one of the things that we do in our program is to collect data and develop the tools necessary to ensure that we develop and implement processes and policies that minimize climate risks and optimize the maintenance of our assets. We do that via climate data collection and analysis, including performing vulnerability assessments, and has recently included developing a methodology for assigning criticality to the MDOT SHA-owned roadway network. So in 2014, we were actually funded to complete a pilot where we did climate change vulnerability assessment to identify specific roads and bridges most vulnerable to flooding in Anne Arundel and Somerset counties. And it was our asset management pilot project that was then funded a second time, where we sought to expand and refine the vulnerability assessment for bridges statewide by applying indicators based on the FHWA vulnerability assessment scoring tool, or the VAS tool, to develop vulnerability ratings for all bridges. And for this assessment, we'd applied indicators based on, this approach used data on asset location and other attributes to serve as indicators of each of the components of vulnerability, including exposure, sensitivity, and adaptive capacity. And the assessment approach used scores assigned to each indicator to develop an overall vulnerability score for each asset across 3 climate hazards: sea level change, storm surge, and precipitation. We also sought to identify specific opportunities to integrate vulnerability assessment results and other climate risk information into processes at MDOT, including asset management, planning, and operations. And the results of this pilot study were actually outlined in a final report, which is named the Integrating Extreme Weather and Climate Risk into MDOT SHA Asset Management and Planning document. And actually, in terms of results of the results of the bridge assessment, vulnerability assessment, we found that about 33 of the 8,500, little more than 8,500 bridges structure studies were vulnerable to sea level change. 172 of those were highly vulnerable to storm surge. 102 of those are highly vulnerable to precipitation change. And assets with a high vulnerability to sea level change and storm surge are concentrated in districts on the eastern shore of Maryland and on the Bay, which is the kind of easternmost part of the state. And assets with a high vulnerability to precipitation change are spread across the districts, with the highest concentration of those being inland. So we use the results of similar statewide road vulnerability assessment to develop a hazard vulnerability index, or HVI, which actually provides a comparative risk value for road segments to climate change variables, including sea level rise and precipitation events. And in that study, it was found that nearly 100 miles of roadway are expected to be permanently inundated by 2050, mostly in Dorchester and Somerset counties, which are on the eastern edge of the state. And the numbers are even higher if you look at the amount of roadway that would be flooded at high tide or mean high or high water. There, we go from nearly 5 miles of flooded roadway at high tide today to over 290 miles by 2050, which is a nearly 60-fold increase. So in our program, we'd also piloted another vulnerability assessment methodology at the corridor level. Namely, it was for the Maryland 450 US 50 corridor to demonstrate a quantitative process to support Maryland State Highway in implementing a quantitative risk assessment technique for incorporation into our risk-based asset management program and to improve system resilience. The purpose was to demonstrate application of the risk and resilience for highways analysis framework derived from the RAMCAP framework, which is the risk analysis and management for critical asset protection framework. And the pilot was intended to directly support MDOT's asset managers, providing an objective methodology to prioritize critical assets and corridors by analyzing assets, threats, vulnerability, and consequences within that risk and resilience framework. Quantitative risk assessment information generated from the process was intended to assist asset managers in determining high risk or high criticality assets within the study corridor, and risk reduction or resilience improvements provided by potential maintenance activities and design alternatives to support performance management activities. So we worked with our consultant, which was AEM, to assess the criticality, to define, what we want kind of our criteria to be for assessing the criticality of our transportation network. And that incorporated several factors aimed at reflecting usage, redundancy, detour lengths. And the assessment was limited at this time as part of the pilot to state-owned facilities. And we developed a model. And in this model, we'd indexed 4 or more GIS layers and assigned the sum of the indices to each segment within the road. We also, we visualized, well, let me go back. So to expound on this actual study, so we did criticality assignment using a GIS methodology for that, but we also did, we found that in using this RAMCAP-like framework, we assessed the assets that could be essentially found within the cross-section of the roadway, any part of the roadway in this corridor, and we assessed the risk, the vulnerability basically to those assets and to drainage assets, namely pipes. And it was found that essentially through what we would maybe define as midterm mitigation and maintenance activities, that we would be able to kind of mitigate for potential climate related risks, including extreme precipitation. So we could, if we made a certain amount of kind of treatments and we did some different things and upgraded our system a bit, the benefit would much outweigh in terms of dollars and user risk and owner risk. It would much well outweigh the benefit of leaving as is and kind of replacing on the back end. And so we actually visualize the results of all of these assessments in the M.SHA Climate Change Vulnerability app, which is an ArcGIS Online or AGOL web application that showcases geospatial data products related to climate change and the potential impacts to the state of Maryland's transportation infrastructure. The purpose of the application is to support those in management, leadership, planning, as they make efforts to avert and mitigate potential impacts of sea level rise. So in this particular slide, we have, just to give kind of a 30,000 foot view, if you will, of kind of the data we have. We have, for example, one data set is nuisance tidal inundation, which is based on kind of the latest LIDAR data that we have using flood depth grids, showing projected impacts of nuisance flooding associated with the 2020, 2050, and 2100 flood depth projections for sea level. We have in the next slide our data set showing flood depth grids based on LIDAR data, showing the projected impacts of mean sea level and mean high water storm event scenarios for years 2050 and 2100. And these flood depth grids include projected still water depth information for the storm event scenarios, the 0% annual chance event, 10%, 4%, 2%, 1%, and 0.2% for 500-year storm. Another data set we have is the roadway inundation or flooded roadways data, which consists of linear geometric features for the roadway, which represent the geographic extent of roadway segments projected to be impacted by mean sea level and mean high water storm event scenarios for the years 2015, 2050, and 2100 for those same storm events I'd listed previously. We also have, if anyone recalls, Hurricane Florence hit the state of North Carolina in September 2018 with devastating impacts. And the event caused concern amongst coastal communities throughout the state of Maryland, especially considering that it was expected that the hurricane would make landfall in Maryland, and it just happened that we were missed. And so we thought it'd be a great idea to model those potential impacts that we could have seen had it actually made landfall. And so we modeled roadway inundation associated with that level, that storm, inundated parcels, and flood depth grid data. We also have, at this time, I think we're at about 113 layers. And so we have a variety of other climate change related data products that have been included for display in this application, and they include like a myriad of things, including FEMA, hurricane evacuation routes, roadway federal aid eligibility, state emergency roadwork events, critical areas, floodplain data, just a myriad of data that makes it usable and makes it accessible and makes it a useful tool for a number of customers. And so I think that is the end of my presentation. I could turn it over to Courtney.
Okay, Courtney, I know we had a little bit of discussion that was planned for this, but given the time, why don't we just go straight into the questions if you want to moderate the questions?
Sure. I do have a few questions. Most of them came in through the chat, but I'm going to start with the one that is in the Q&A, and it's from her question is, are the assets owned by local jurisdictions included in the vulnerability assessments? Or does Maryland DOT provide support to do so in parallel?
We do include assets owned by other roadway and bridge assets owned by other jurisdictions in that assessment. The criticality is relegated to MDOT/SHA owned assets only, roadway assets only.
Okay. And within the chat, we have a question from Matthew Long. For coastal roads that you know will be underwater soon, how do you choose between elevating the roadway versus retreating? Will every roadbed become a de facto levee?
I think that may have been for you, Toria, but I don't know if you want to answer or how you want to.
That's not necessarily a decision that that we make. That's something that kind of how to treat it maybe can be finalized through like a collaborative effort between the state and local jurisdictions and the public. But it's on us to be transparent about what the expectations are, what the kind of climate projections are, and make sure that we're all on the same page about knowing what's within the realm of possibility and feasibility given what we're anticipating.
And just out of curiosity, someone wanted to know if your study is publicly available. And if there's a link, maybe you can or link to resources or related resources, you can probably copy that into the chat. It's up to you.
The study is not publicly available, and I'm not exactly sure when it will be publicly available.
But the application is publicly facing, and that is actually the link is on the slide. We can copy that into the chat as well.
Yes, I can. And also I'd like to add, thank you, Sandy Hertz, for adding in terms of how to kind of decide how we treat county roads. She pointed out that it also boils down to whether it's an acute event or a chronic issue. That is a major factor.
So those are all the questions that I have in front of me. Our time is winding down. I don't know, Bill, if you, Terry, if you wanted to continue with any discussions, but kind of leave that up to the panel.
Yeah, I think given the time, I'm one of the issues that I did want to cover that I don't think we have time for, but certainly is, just the way in which, or the difficulties that we really can take some of these processes and these analyses, and how do we incorporate them into our day-to-day planning and maintenance and design processes, and the difficulty of doing that given the fact that these are bounded probabilities and there is some level of uncertainty. I mean, with pavement, we have pretty good models of when we need to do maintenance. This is a little different, and so anyway, I mean, I think that's a big challenge, but we'll take that up on another day. So I think we have run out of time.
We have, and I'll just wrap it up really quick with a thank you to all of our participants today. And just as a note, you will receive an email from the NAEP office within 1 or 2 days. That'll include the webinar recording, along with a brief survey, and we would appreciate your participation in that survey. And thanks again, everyone, for your time today.